Okay, good morning, everybody. So my name is Nathalie Job. I'm professor at the Department of Chemical Engineering at the University of Liège in Belgium. I was a reviewer for this thesis, but I will also have the pleasure to act as president today. So I will first introduce the jury of this thesis. So we have the pleasure to listen to Eleni Effraimopoulou today. And the jury is composed by Aurélia Charlot from INSA Lyon, Sylvie Callas, maître de conférence à l'Université de Montpellier online, Merima Hassani from Chalmers University of Technology in Sweden. Then we have Wim Malfay from EMPA in Switzerland, Zurich. Then Gino Mangente from Cargill. And then the people who directed the thesis. So we have Julien Jaxel. We have also Arnaud Regacci and Tatiana Woodtova. So Mrs. Effraimopoulou, you will have 40-45 minutes to present the work to the audience, and then there will be a question from the jury, obviously. And yeah, we're listening to you.
Thank you very much. Okay, so thank you everybody being here today. Good morning, everyone. I will present you today my work on pectin-based aerogels for thermal superinsulation. This work is a joint project between PERSE and CMF institutes from École des Mines de Paris, and it's in the frame of the Transition Institute 1.5. So I will start by introducing you in the topic of my work. Then I will share with you the main results that we obtained, and we'll close with the conclusions and prospects of this work. Starting with the introduction, we know that we face a big problem nowadays with energy consumption, and we have a huge energy consumption coming from the building sector that is consumed for heating and cooling, and this is mainly to insufficient thermal insulation. The most common insulation materials used have thermal conductivity in the range of 0.03 to 0.04 watt per meter Kelvin. And the lower is the thermal conductivity of the material, the better is the insulation efficiency that they have. At 0.025, we have the thermal conductivity of air, and all materials that possess lower thermal conductivity are considered to be super insulating. In this area, the only solid materials that we can find are aerogels. What are aerogels? Aerogels are open pore nanostructural materials that have high surface area, they have very low bulk density, and they have a very high content of porosity. They can have different chemistry, structure, and shapes. And right now we can find commercially available, not in the neighborhood store, let's say, but we can find silica aerogel blankets that have the lowest thermal conductivity. The lowest thermal conductivity that is available for commercial products at 13 milliwatt per meter Kelvin. However, they are very expensive and they have poor mechanical properties. And for this reason, more lately, synthetic polymer aerogels were fabricated to overcome these problems. However, they have a bit lower performance, so higher thermal conductivity. What we want to do is to pass to biopolymer aerogels, so to have natural products that are non-toxic, biodegradable, and come from waste for valorization. Let's see how biopolymer aerogels which are biopolymer aerogels. Usually they're from polysaccharides, protein, or other polymers coming from biomass. And from this family of materials, we know that pectin aerogels possess one of the best properties regarding thermal insulation. We can see here that for a range of formulation, we have super insulating properties, and we can reach down to 15 milliwatt per meter Kelvin, so much below air. Pectin is usually extracted from citrus peel and apple pomace that comes from waste from the industry. It's a natural heteropolysaccharide. It's water soluble. It's used in the food industry as for its gelling properties, and these properties depend on the degree of esterification of pectin, on the pH of the solution, and other parameters. Pectin, because of its structure, is very highly hydrophilic, and when we want to use it for materials engineering, we notice that there is a very rapid aging, and probably not to see with a lot of biopolymer aerogels, and we have loss of the insulation performance that we can see in the graph above. So the first question that we have in my thesis is how to make pectin hydrophobic. Next, a very important parameter for aerogel materials is the drying technique that we use to obtain the structure. We start from a solution in general for aerogels, creating a gel and then drying to obtain the final aerogel. We can use evaporative drying. In this case, we have huge capillary stresses on the walls, and then we obtain very dense structures like this. We can use freeze drying, where we freeze the solvent and sublimate from the pores of our gel. And in that case, because usually water is used as solvent, the ice crystals that grow lead to these big pores inside our material. Lastly, we have supercritical drying, and we refer to these materials as aerogels in this thesis. And in this case, we eliminate the capillary stresses in our structure, and we can obtain a very fine nanostructure network. And we can see here in this picture that we have very small pores and a very nice structure with fine wads. There is work done to bypass supercritical drying and obtain materials with good properties by evaporative drying, and only for silica and cellulose these have been achieved so far in the literature. So the next question is how to make aerogel-like pectin materials without the use of supercritical or evaporative drying, or freeze drying, sorry. So with evaporative drying. The goal of my thesis is to have a super insulating material, and starting from pectin aerogels that we know that have very good properties in terms of insulation. We want to use it for energy applications, mainly focused on buildings and construction as thermal insulation, but a lot more applications. Our goal is to have a material that is bio-based, non-toxic, is durable, is thermal super insulating. It comes from green chemistry roots, and it's cost efficient, so it can be implemented in the everyday life. For this reason, as I mentioned before, we need to work on the properties optimization of our materials. So we need to hydrophobize pectin to prevent aging. And next, we need to work on the process optimization in order to avoid supercritical drying and reduce the cost of our final material. When I started my thesis, we had a very big gap in the literature considering this topic. So in general, for pectin hydrophobization, there are practically no works. There are some modifications, still not allowed, but nowhere is mentioned hydrophobicity of aerogels or pectin itself. Then there are no data about aging of bioaerogels. In few publications, some people mention 1 day of aging, and it was never successful to keep the properties. And then for avoiding supercritical drying, we only know for bio-based aerogels, for cellulose, one work with specific fabrication process. So we needed to start from this. And what can we do to meet our goals? Here is the general scheme of pectin aerogel fabrication. So we start from a pectin aqueous solution. We create a gel by non-solvent induced phase separation, and then we dry with the supercritical carbon dioxide to obtain our aerogel material. We had different approaches, so we could work in all different steps of the synthesis. We tried to work with the dry aerogel, and in this case, we performed chemical vapor deposition of silica phase. Then we've worked on the organogenesis phase so that we can keep the structure after coagulation and obtain the superinsulating properties. And we did modification with isocyanates and modification with amines. And we've worked also on the pectin solution in order to optimize the process to avoid supercritical drying, and this by doing the coagulation in alkaline media. Let's start seeing some of the results. So starting with the pectin silica composite aerogels, we did chemical vapor deposition of methyl trimethoxylane on our final aerogel. So we worked on the dry material, and for this work we used high methoxypectane. We can see here the aerogels were placed in a closed container with the reactant and the catalyst, and they were left so that the silica phase can be developed. And we varied parameters, we varied different parameters as the initial concentration and pH of pectin solution, the non-solvent used for coagulation, and the duration of chemical vapor deposition. Now, I will give you an example for one formulation, starting from high methoxypectane solution of 2.8% at pH 2. This is the properties of the neat material. So we see low density, high specific and low thermal conductivity. And after 24 hours of chemical vapor deposition, we see that we have a huge increase in bulk density and a decrease in surface area. However, we get hydrophobic materials, which was our goal. We saw, when we see the structure with scanning electron microscopy, that inside our network, we had the formation of some silica nanoparticles, which appear to be non-dense, as we saw also for the surface area values. So we wanted to adjust our process to avoid the formation of these baits. We tested to see if the silicon was distributed in the network. So from interior pieces of the material, we could see that silicon was very homogeneously distributed. So the reaction could reach all the parts of our material. We continued further by adjusting the duration of chemical vapor deposition, and again for the same formulation for this formulation. 2 hours, 5 hours, and 16 hours. Okay. And for this case, the bulk density is increased when we have high deposition time. The surface area is decreased. Thermal conductivity increases as well. The contact angles, we can say that they stay almost stable regardless the time. But when we see the contact angles in time, not the contact, we see that when we have 2 hours of deposition, the contact angle is decreasing a lot and the droplet is eventually adsorbed from the material. In order to evaluate if our materials are stable in moisture, we do aging studies in 25 degrees and 80% relative humidity. We see first the neat pectin aerogels. So we can see, as we expected, that in the first day in these conditions, we have a huge increase. We have the most increase. We have moisture uptake around 15%. Then we have a huge increase in bulk density. So we have 8 times the value. And this happens the first day, and then it continues to increase. And the same happens for thermal conductivity. So as we said, the unmodified pectin aerosols cannot be used as insulators as they are. When we do the deposition of the silica phase, we can see that the moisture uptake decreases a lot. So it's almost half. Then the bulk density increases slightly in the first day, but stays rather low compared to the neat pectin aerosols. And the thermal conductivity increases more substantially. This is the red line when we have 2 hours chemical vapor deposition, and for 16 hours deposition, the thermal conductivity stays nearly stable for the whole duration of the test, that was around 250 days. So in general, we saw that for the composite materials, we have better stability, and we have lower moisture uptake and density increase when we have a longer deposition time. And for 16 hours chemical vapor deposition, we have stable thermal conductivity. However, we're not in the superinsulating area. Coming back to our objectives, for the properties optimization, we wanted to obtain hydrophobic, non-aging, and superinsulating materials. And for the pectin silica composites, we were able to achieve the first two goals, but not to get the superinsulating properties. Now, the next approach that we had is to modify aerogels to graft the aerogels, and this was by modification with amines. In the general scheme now, we've worked with the organogel. So we are in heterogeneous reaction, and we used low methoxypectin at 3 weight % and pH 2 from the initial aqueous solution. Here we can see the reaction that is performed. So first step reaction was carbonyl dimidazole to activate the functional groups of pectin. And second step, we add an amine. We varied a lot of parameters for this reaction. So first we varied solvent duration and amount of CDI. And for the second step, we varied again the solvent, the duration. We used 5 different amines and also the amount of amine that was used. So first we optimized the conditions. We did a lot of test experiments, and we used the conditions that are mentioned there for the further studies. And we can see here the effect of the size of the side chain of amine on the degree of substitution of our materials. And also we can see the different solvents, how they affect the degree of substitution. So in general, we had lower degree of substitution when we were using bigger amines, and we have the highest substitution for acetonitrile. Looking at the hydrophobicity of our finer aerogels, we see that even though we had lower substitution with big amines, we had higher hydrophobicity, which makes sense because we have more lipophilic chains in our material. Some examples of materials that were super insulating and with increased contact angle, modification of the aerogels in acetone and tert-butanol. So with butylamine in both cases, here in acetone, here in tert-butanol. In both cases, we have low density, we have high specific surface area, very close to our neat materials. Contact angles are increased a lot. Here we're almost hydrophobic. And the thermal conductivity is remained very low, so as low as we have for neat pectin aerogels. However, we had a lot of challenges with this work, which is good and bad. So first, we noticed that the substitution was not homogeneous. This we saw with FTIR. So we had a higher substitution on the surface of our aerogel and lower as we were going inside the material. Then we saw that we had some structural changes at the end. So we expected to obtain at the end the structure since we had performed already the coagulation of our material, but we saw that during the reaction our gel was changing, and this was not good always for density and thermal conductivity. And lastly, we saw that we lost a lot of mass during the modification. So when chains started to substitute a lot on the exterior of our material, they started to dissolve in the solvent. And for these dissolved chains, we could estimate a very high degree of substitution. So for these materials, in general, we could achieve enhanced hydrophobicity. We could reach very high contact angles, even with not as high degree of substitution. We could preserve the thermal conductivity of the structure if we had preservation of the network during the reaction. Then we could achieve a very high degree of substitution, but only for the dissolved chains. And it opens a very big door to produce derivatives of pectin with controlled degree of substitution. Coming back to our objectives for this family of materials, we could achieve the hydrophobic character. We could obtain the superinsulating properties, not in all cases, but it is feasible. And we don't have the aging data yet because of time constraints. Next, last strategy to prevent aging was to prepare pectin polyurea composite aerogels. In that case, we did modification with isocyanates, and we worked with organogel again as a heterogeneous modification. For this work, we used the low methoxypectin at pH 2. And here we see that we used the 3 different triisocyanate molecules that can be grafted on the pectin fibrils and then polymerized to create a polyurea network. We had these 3 parameters, so I will be referring to them as polyurea 1, polyurea 2, and polyurea 3. And we varied for this project the concentration of pectin in the starting solution and the concentration of isocyanate to get different content of isocyanate inside our material. Let's see first the influence of polyurea nature on our materials. We can see that the bulk density was low for all materials, but it was higher for the first and second type of polyurea used. Then the specific surface area decreased from the neat materials to the first and second type of polyurea. However, it stayed always in higher values for the third type of polyurea. The thermal conductivity was not really affected, so we see that the values are very close to the ones of the neat pectin aerogels, and we are satisfied with this. And lastly, to evaluate the hydrophobicity, we measured the water contact angle, and we can see that for the first 2 composite materials, we have increased the hydrophobicity of our structure, but we're still not very hydrophobic, so we're below 90 degrees. However, with the third type, we are hydrophobic. Looking at the structure of our material, we cannot really see a difference. So the first picture is the neat material, and then there are the other composites with similar concentrations. And we cannot see a secondary network or any particulate form. So we suppose that we have a nice coating around our pectin fibrils. Overall, we concluded that the third type of polyurea worked the best, so we decided to go with it. And also, we tested the aging and we saw that it had better stability in moisture. So going with the third type of polyurea aerogels, we wanted to see what is the influence of polyurea and see how much we can reduce the synthetic polymer inside the material. And we worked with polyurea content from 20 to 45% in the dry material. We saw that the variation of polyurea content didn't really affect the bulk density, surface area, thermal conductivity, but we had the we had an effect of contact angle. So the materials were hydrophobic only when polyurea was more than 30% inside the material. We did aging studies in the same conditions as before for at 25 degrees and 80% relative humidity. When polyurea content was increasing, then moisture uptake was decreasing and bulk density increase was lower. For the thermal conductivity, we can see that when we have 35% polyurea in our material, then we have still, after 120 days, superinsulating properties, but only for 45% of polyurea, complete stability was reached. So for these materials, the thermal conductivity was 0.015 watt per meter Kelvin, and we have extended study than this, and we see that it's stable for after 300 days almost. And since they were the most promising materials, we tested also mechanical, acoustic, and fire properties. Very first results that I don't have time to discuss with you in the presentation, but they seemed very interesting and promising. Coming back to our objectives again, last point for the process optimization was the pectin polyurea polyurea composites. And in this case, we were able to tick all of our first objectives, to have a hydrophobic network that is not aging and super insulating materials. So now we'll go to work on the process optimization. And in order to avoid supercritical drying, we try to do pectin coagulation in alkaline environments. So now that scheme changes a bit, there is a new leg here, adding evaporative drying in order to receive zero gel materials. So when I say zero gels, I always refer to materials dried by evaporation and aerogels by supercritical drying. We worked on the pectin solution and we added base, and we used both high and low methoxypectin. We worked with different concentrations of pectin, 2 different bases for different concentrations of base, and we saw how the drying method is affecting the material properties. So first, we see the properties of the aerogels. Some examples are here. So in red on top, there is low methoxypectin, LMP, and blue high methoxypectin, HMP. And we see that there is not a real trend. The densities are relatively close to each other. They're in low levels. Then for the specific surface area of our materials, we see that when we add a small amount of base, so we are in close to neutral pH values, then we have a very high specific surface area, and the properties of our materials are very close to the ones obtained in acidic conditions. Then when we start to add more base, we go to alkaline pHs, and we see a huge drop in specific surface area. And after a point, we don't really see a big difference inside the experimental error. We can see these properties depicted on the images of our structure from scanning electron microscopy. So here we are in the low concentration of base, so in the very beginning. We see we have small pores and a very fine structure, and here we see the structure at acidic conditions. So if you put it one on top of the other, you'll see that they are very, very close. But then when we go to higher pH, more base in our system, we see that the structure changes. We have thicker fibrils in our network, and the pores start to be bigger. So for the aerogel materials drying with supercritical drying, when we increased the concentration of base, we didn't have a real effect on bulk density, but then we had a huge decrease of specific surface area, as we can see also from the structure. Coming to the properties of the zero gel, so dried by evaporation, we see a huge effect on the bulk density, depending on the concentration of base. So again, high and low methoxypectin. When the concentration of base is very low, we have very, very high bulk density that is close to the density of pectin. And as we increase the base in our system, we reach values that are very low. Then the specific surface area starts again with lower values, and as we increase the base concentration, they reach values up to 270, 80%. Not percent, sorry, 270, 280. We can see the structure again. So in this case, when we have very, very high bulk density, we can see the structure of our material that is very dense. We cannot really see the porosity. And when we go to high base concentration, we get a very nice structure. Not as nice as acidic pH maybe, but we have very open pores and well-defined fibrils. And and you can see the dust lines here are the properties of the aerogel materials. So when we're in high base concentration, the dust lines that are the properties of the aerogel materials are almost overlapping. So when we're in high base concentration, the properties that we get by evaporation and by supercritical drying are very, very similar. So for the zero gel materials, when we increase the concentration of sodium hydroxide, we have a decrease of bulk density. We have an increase in specific surface area, and we tested the thermal conductivity of the materials that showed the best surface area and bulk density values, and we saw that it was between 0.03 to 0.035 watt per meter Kelvin, which is not super insulating, but is very low still. It's it's in the level of the insulation materials that are used right now. Most importantly, the most important fact was that when we had a high concentration of base, we could obtain the same materials by evaporation as we could by supercritical drying. So coming back to our objectives for the last time, working on the process optimization in order to avoid supercritical drying, we made the aerogel-like pectin by coagulation in alkaline media. And we could achieve avoidance of supercritical drying. However, still we not have super insulating materials. Coming to the conclusions of my work, we started with pectin aerogels that we were very fascinating that they could be used inside the buildings as they come from the food. And we saw that not they only have super insulating properties, but they can transform in eco-friendly materials that are super insulating, that can be stable in moisture. And for us, this is a very big step to advance this kind of materials. We had to work with two disadvantages, so the moisture sensitivity and the supercritical drying. We used different approaches, obtaining modified materials, composites, in different steps of the synthesis, and we could separately tackle its problem. Then for the future work, we could say that there is room for a lot of studies. We did the first step to open the door to different families of materials. So for each different family, there are prospects to optimize the properties that we have. Then a general prospect would be to combine super insulation and durability with the avoidance of supercritical drying, so to have all in ones. And of course, other studies to see how they can implement it after environmental impact, economic assessment, and others. This work was communicated so far through one journal article and one working paper. Some articles are under preparation after the presentation. Then in several conferences as poster and oral presentations. And most importantly for me was the international mobility. So I had the opportunity to do 3 mobilities, 2 in Vienna, in Boku University, and 1 in the University of Athens, with some results you saw in the presentation. And last but not least, I would like to thank everyone. I'm very grateful for all the collaborators we had from all different departments for different properties, ideas, discussions. I cannot name one by one the names. The funding agencies, the Transition Institute. We thank Cargill a lot for providing materials, discussions, and for analyzing some of our samples. And thank you very much for your attention.